Hi, my name is Alicia, and I will be presenting our work on a dataset and simulator for the vision-based aircraft detect and avoid problem. While we have built this benchmark around a specific application, we hope that the impact of this work will span beyond this problem and serve as an example for other real-world high-impact applications. To provide a brief overview of the problem at hand, vision-based aircraft detect and avoid involves detecting intruder aircraft using images from a mounted camera and selecting a collision avoidance maneuver based on the detection. Here's a closer look at what the detect and avoid process looks like from the point of view of our controlled aircraft, which we call the own ship. You can see in this graphic that the own ship begins on one trajectory and then adjusts upon detecting the other aircraft, which we call the intruder. The dots on this plot show the 17 points at which the own ship detected the intruder, which you can see is associated with the decline in altitude out of harm's way. The original trajectory would have resulted in a mid-air collision, which in a real-life scenario is likely to result in catastrophic damages and potential loss of life. The aircraft detect and avoid problem is an example of an incredibly high-risk application that exemplifies the need for extensive and robust evaluation before models can be put into use. Here's where our work comes in to serve as an example of what a robust evaluation system might look like. The avoids benchmark consists of three main components: a dataset, baseline models, and evaluation capabilities. We cover evaluation on both a test set and in a closed-loop simulator, allowing us to test the intruder detection model both on isolated examples and on the downstream task it is meant to serve. The dataset and trained model represent the first major contribution of this work. We used X-Plane 11, a photorealistic flight simulator, to generate a dataset of 72,000 images of mid-air aircraft encounters. The images depict 6 different levels of cloud covering, 3 aircraft types, and 4 geographic regions with a randomized time of day. Since X-Plane 11 outputs ground truth information about each aircraft displayed, we were able to auto-calculate exact bounding boxes, removing the need for manual labeling. Using this dataset, we trained a YOLO object detection model on the task of locating the intruder aircraft in the frame. We also trained an alternative model on nominal conditions to compare the performances between training sets. The alternative model was trained on about 7,000 samples, which only consisted of minimal cloud cover between 8 a.m. and 3 p.m. local time. The dataset includes a broad range of environmental conditions, as well as annotations that describe the conditions depicted in each image, allowing for more complete training and testing of aircraft detection models. We also provide code for producing datasets with custom conditions that can be used for custom training and evaluation. The second major contribution of our work is the evaluation suite, consisting of standard metrics like mean average precision on individual samples, as well as evaluation on the collision avoidance task. To evaluate the model on the downstream task, we developed a closed-loop simulator that uses our trained models as part of our perception system. The initial aircraft trajectories are determined by a straight line encounter model that outputs step-by-step positions of the 2 aircraft over 50 time steps. All encounters generated would result in near-midair collision without intervention. The simulator captures an image and feeds it into the aircraft detection model and outputs the estimated intruder position. Based on what the model detects, the controller uses a control policy called vertical CAS to issue an advisory to the own ship on what action to perform to avoid a near-midair collision. The own ship then takes that action and both aircraft's locations are updated. The perception system then runs again to determine the next appropriate action. We go into deeper discussion of the evaluation results in the paper, but we provide a brief overview in this presentation. The key insights we draw here is the importance of training on a large and highly representative dataset. We saw a clear difference in performance between the baseline and alternative models overall, with the baseline model exhibiting a mean average precision of 0.86 across all categories versus 0.76 for the alternative model. We also see that for the alternative model, which was only trained on images from Palo Alto, there was a significant drop in performance for the other locations, for which the baseline model performed more consistently. Over 8,640 simulated encounters, we found that the baseline model results in far fewer near-midair collisions than the alternative model, again demonstrating the importance of training detection models like this on a wide range of conditions. However, we do see some differences in trends between the downstream task evaluation and test set evaluation that show the potential harms of relying on test set evaluation without considering real-world metrics of success. Thank you for watching and listening. Please feel free to reach out if you have any questions.